If you cannot trace one user request end-to-end, you cannot debug your LLM feature. Add correlation IDs and minimal tracing. You feel lost when a request fails. Logs from different services do not tie together. I will show a tiny, deterministic tracing pattern that makes a single run findable and measurable. You will be able to follow one request through token accounting, latency estimates, and a simple cost estimate. That view turns random failures into reproducible stories you can fix. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Tracing an LLM pipeline is mostly an engineering pattern. The pain is not lively math. It is missing context. A user reports bad output. The model call happened 5 services ago. Correlation IDs are the glue. Minimal console traces give you a low-friction timeline. Success looks like a short log you can hand to a teammate and have them reproduce the run. At a high level, we want 2 things. First, a stable handle for each request that survives retries and restarts. Second, a short per-step record with token counts, estimated latency, and cost. That is enough for incident triage and early optimization without a full observability stack. It scales from single experiments to moderate production traffic because it is cheap and deterministic. We will build a tiny tracing scaffold you can drop into a notebook or a service. It uses simple string math to make repeatable IDs, a trace list to collect step metrics, a token count heuristic based on whitespace, a small per token latency model, and a cents per 1,000 tokens rate to estimate cost. Nothing here needs network calls. That makes the pattern easy to test and safe to run in CI before you wire it into real model calls. Now we start the scaffold and create a run handle. This snippet creates a deterministic correlation ID and a trace store. We start with a tiny prompt string that anchors the run. The variable total sums character codes so we can derive a stable, repeatable ID without randomness. The variable run ID turns that sum into a 0-padded hex string, giving us a compact correlation handle. The list trace will hold per-step metrics we add later. The printed run ID is the stable handle to tie all steps of a run in logs and consoles. This approach is intentional. By deriving the ID from the prompt, you get repeatability. Tests can assert the same run ID for the same input. And because the trace is just a list, you can serialize it to JSON, print a single line per step, or forward it to any logging backend. Next, we simulate a single model step and capture token counts. This snippet records a single LLM step's token counts with a step ID. The variable step ID names the operation so we can trace it later. The variable resp mimics a model transform by uppercasing the prompt, giving a predictable output. The variables tokens in and tokens out count whitespace delimited words to approximate token usage. We append a metrics dictionary to the list trace, so later steps can compute latency and cost. The printed step, input tokens, and output tokens show how much this step consumed. That simple approximation is not a perfect tokenizer, but for tracing, it gives you consistent signals. If you swap in a real tokenizer, the shape of the trace stays the same, and your downstream math still works. Now we add deterministic timing estimates and find the slowest stage. This snippet estimates per-step latency and flags the slowest step. The variable ms per toke sets a simple per-token latency model to avoid non-deterministic timing. We update the last trace entry with an estimated milliseconds from its input and output tokens. Then we simulate a lightweight post-processing step, compute its ms, and append it to the trace. The variable slow selects the entry with the highest ms so we can see where time is going. Increasing milliseconds per toke raises both step times. Decreasing it lowers them. The printed slowest step highlights the current bottleneck. This gives you a quick way to prioritize optimizations. If a small post-processing step looks heavier than the model call, you might move it downstream or optimize its algorithm. Next, we convert token counts into a simple cost estimate. This snippet converts tokens into estimated cost for the run. The variable rate encodes a cents per 1K tokens price, so we can estimate spend without coupling to a vendor. The variable tot sums input and output tokens across all traced steps, tolerating entries that only have latency. The variable cost multiplies total tokens by the rate and scales by 1,000 to get cents. Increasing rate models a pricier model and increases the printed value. Decreasing it does the opposite. The printed total cost cents shows how much the traced steps would cost. This is a helpful, lightweight guardrail before you run large batches. It also lets product and finance teams see the back of an incident and make quick decisions. Finally, we print a compact console summary for incident debugging. This snippet prints a compact console summary for the whole run. The variable steps counts traced operations, so you know how many stages executed. The variable lat sums per step latency estimates to reveal end-to-end time. The variable tokes aggregates input and output tokens across steps, giving a basis for spend. We reuse costs from earlier, so the summary lines up with your pricing assumption. The printed summary gathers what you need for incident-style debugging: step count, total latency, total tokens, and total cost. A single-line summary like this is what you want in a paged alert or an initial bug report. It answers the question what happened and where to look next. In a real system, this tiny scaffold maps onto request middleware or a client wrapper. The run handle becomes a header that follows the request through your services. The trace expands with each service that participates. You keep the same math and the same printed summary, so everyone reads the same story. Recap. What it is: a minimal tracing scaffold that combines a deterministic correlation ID with per-step console traces for tokens, latency, and cost. When to use it: during development, incident triage, and lightweight production observability before you adopt a full tracing system. One caveat: the token counts and latency are estimates. Swap in real tokenizers and timings when you need accuracy. Next step: scale the same approach to a batch of requests and add timing measurements from production, so you can compare estimates to reality. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.